Welcome to lecture 13. In this lecture I'm going to talk about small oscillations of things that are not springs. Turns out that even things that are not springs are actually really well modeled by simple harmonic oscillations, or in other words by a mass on a spring. So it's exactly what I'm saying here. Mass on a spring provides a good model for a lot of different processes that are essentially any form of oscillation, provided the oscillations are sufficiently small. Now, how small is small? That depends on the particular system we're analyzing, but we'll discuss that and we'll come to understand what this is actually saying, and we'll go through some examples. Let me show you what I mean first. Here's just one example of a small oscillation. That's not a spring. I've got a ruler here, hold it against the edge of my desk, and I'm just going to do this. You can tell it's vibrating very fast. Let me do it again. It's a vibration, an oscillation. It's not a spring, it's something completely different, and yet the motion is well represented mathematically by a spring. So here's then a picture of what you just saw. I've got a table, I'm putting a ruler on the table. In my picture the ruler is just horizontally sticking out. I'm clamping it down with some weight or my hand, or it doesn't matter what it is. And then just by flipping it, by pulling the ruler down and go, it'll oscillate up and down fairly fast. So the ruler wants to be in this position here in the middle. So that is my equilibrium position. When it's up here, the flexible elastic force in the metal, again, the details here are complicated. It has to do with the elasticity of the metal, how easily does it bend, ultimately its molecular structure. I don't know much about that. What I can see is that the force up here is downwards, elastic force downwards. Whereas down here, the force is up. By bending it down, it wants to go back up. What happens? It reaches the equilibrium point, but it has some speed, it has some momentum, it gets so it overshoots, slows down, and oscillates back and forth. So the elastic force in the ruler is a restoring force. It points towards an equilibrium position, while at the equilibrium position there is no force on it. Now, is this a linear restoring force? Probably not. I have no reason to think that it would be. But maybe it can be approximated as a linear restoring force. So let's look at that in a bit more detail. So drawn here I have two major characteristics of simple harmonic motion. As mentioned, there's the linear restoring force, right? So if I plot the force against the displacement, it's going to look like this. It is a negative slope, goes through 0, and it's a straight line because it's a linear restoring force, meaning twice the distance, twice displacement, twice the force. If the object is displaced to the left, the force is to the right. If the object is displaced to the right, the force is to the left. And so negative displacement means positive force, positive displacement means negative force. Second way to think about simple harmonic motion is in terms of the potential energy, and as you know, the potential energy goes as x squared. It's a half kx squared specifically. And so the graph looks like this. It's symmetric left and right, and the crucial thing to note here is that the equilibrium point, it has a certain value. Now here the value is given to be 0, but that's not very important because I could just shift the whole graph up and down. It doesn't do very much because only ever potential energy differences matter. What's crucial though is that the slope right here is 0, right? It's flat. Specifically, it's not just flat, it's a minimum. The function of the potential energy against displacement has a minimum at the equilibrium point. So those features, linear restoring force, x squared potential with a minimum here, those are the features we're going to see to apply approximately to lots of other situations. So let's start by guessing what the restoring force for the ruler that was oscillating at the edge of the table, what that might look like. So here's an example of a graph that shows a force against displacement that's not a spring, right? This is not a straight line. But it is a restoring force, because if displacement is to the left, the force is positive to the right. If displacement is to the right, then the force is negative, therefore in the opposite direction of the displacement. So it is a restoring force. It's not linear, it's not a straight line. Now, this could represent the ruler, perhaps. The idea here is that if I bend it too much, actually it becomes really hard to bend it further, the force becomes very big, and at some point there comes a line when the ruler might break. Right? You can't just displace it for as much as you want. There might come a breaking point that's realistic. Same thing for a physical spring, right? A physical spring comes a point when the metal just gets too bent, and it's not acting like an ideal spring anymore. But this is a restoring force. Now, if I focus on the oscillations being small, and we haven't yet defined exactly what we mean by small, but if I imagine it's just a small oscillation left and right, if I zoom in, right, on this sort of segment here, let me zoom in, let me draw this down here, I'm zooming in, you imagine it sort of like this, right, we're zooming in, then just looking at this section here might look something like this. Right, I'm just literally taking this and making it bigger. Now this looks very straight. Right, so this here is well approximated by a straight line. By a straight line, and of course a straight line, that means a linear restoring force. Now, depending on the shape of this function, right, I might have to zoom in quite far to get a straight line. But as long as the function is sufficiently smooth, and it doesn't have like spikes, no matter how far you zoom in, it still has like spikes. You can come up with mathematical functions like that. If there's some degree of smoothness that I'm not going to define further here, then if I zoom in enough, I'm going to be able to find a scale at which I get this kind of picture. It doesn't matter how wild you make the function left or right, how steep, how many mountains you got. There must come a point when I zoom in enough where I can get approximately a straight line. And this zooming in enough, like making our maximum displacement sufficiently small that the straight line approximation looks pretty accurate, that's what we mean by having the oscillations be small. And so, if I only displaced my ruler on the edge of the table a little bit, like only from here, say, to here, not anywhere near the breaking point, then the motion will be well approximated by a linear restoring force, and therefore by a spring. Now, how would you actually find the spring constant in that case? Well, you just take this graph here, and you take this point here, and this point here, say, and you literally draw a straight line. Now, it's already drawn in such a way that they're essentially identical, right? You could imagine that no matter how you zoom in, it's still slightly curved, so this might not be exactly the same. The red line, my straight line approximation, and the actual line, the green one, but it's a very good approximation, so I can just calculate the slope of this as essentially the rise over the run, and so the slope of here gives me the effective spring constant. Right, the slope gives the effective spring constant. It's called effective because it's not literally a spring. It's not literally a spring constant, but it acts like one. So for practical purposes, it is a spring constant. Spring constant. Right. Because up here, of course, the slope of this is the spring constant. F equals minus kx. The slope is minus k. So the steepness of it is k. Same thing here. This is how I approximate it. Let's do an example and see what happens. Here's the example I want to go through. I imagine I've got some kind of mass here, and it's held right between two fixed points with stretched rubber bands. So this is a stretched rubber band here. This is a stretched rubber band here. And what I'm going to do is I'm going to imagine I'm going to take this mass and I pull it up to here, let it go. It's going to oscillate vertically like this. Right? Now the rubber bands themselves, maybe they can be modeled like springs very directly, but I care about this vertical oscillation here. I imagine they're already stretched, right, when the mass is in the middle. So this is not their equilibrium 0/4 length. Right now here there's a tension to the left, tension to the right. Now I'm going to assume that the displacement is small. Let's give this displacement a variable name. Let's call this my y direction. Now imagine I'm looking down onto a table here, so there's no gravity involved in all of this. In fact, it wouldn't change very much, but imagine I look down on a table and sort of oscillating in the horizontal like this. So I imagine that the oscillations are small enough that the tension doesn't change from here to here. Technically speaking, this length here is ever so slightly longer than this. And therefore, if this is a rubber band, it's ever so slightly more stretched than it was here. But if this oscillation, if this displacement up here is small, and probably a lot smaller than I've drawn it, right? If this is sufficiently small, then the length of this is almost identical to the length of this. Let me do a little aside here to justify that. Let me call this length here L twiddle, or L tilde, it's called. Imagine this is length L tilde. So what is L tilde really equal to? It's equal to L squared plus y squared, where this is the y position, right? This is my y direction, and take the square root. This is just the Pythagorean theorem applied to this triangle here. Now I can write this as L. I can take out a factor of L, 1 plus y squared over L squared. Make sure you follow the algebra here, right? I've just simply factored out L squared and take it outside the square root. So that's equal to this. This is exact. And then, because this thing here, right, I'm assuming this thing here is much smaller than 1. That's where the small oscillation assumption comes in. I'm assuming that this distance here is much smaller than this distance. How much smaller? Maybe less than 1% of it. Or maybe less than 1/1,000,000th of it. Or maybe just less than 1/10th of it. Depends on how accurate I want to be. Or I need to be. If this is smaller, you can actually approximate the square root like that as L, right, times 1 plus 1/2 y squared over L squared. So this is an approximation of a square root of 1 plus a tiny thing. If you don't believe me, get out your calculator right now and try the square root of 1.01. Right, so 1 plus 0.01. See what you get. You're going to get something that is extremely close to 1 plus half of 0.01. The smaller this number gets, the better this approximation is. Right, so that is my justification that this is essentially equal to this. Because this here goes as y squared. So if y over L is already small, it's like 100, then y squared over L squared would be 1/10 10,000th, right? So utterly small. So I'm justified in ignoring the length difference between here and here, and correspondingly the tension difference, right? This is a little bit of an aside. It's important to play with those approximations, like to really get a feel for them, try different values, see what you get, see why they work. Okay. So I'm assuming the tension here is constant, right, no matter where the object is, but what obviously changes is the direction of the tension. Here the tension is left and right, here the tension is downwards, so it's not a big angle down, so it's still in a very similar direction, but what has changed significantly is the vertical net force, because here there's 0, here there is something. And no matter how small this something is, it's infinitely bigger than 0. Right? So the vertical net force that's here but isn't here, that is something I can't ignore. Let me draw a free body diagram. I've kind of drawn it there already, but let's just draw it again. So I've got tension in this direction, I've got tension in this direction. Right, that's it. I mean, there's pretty weight and normal force, but they're into the page and out of the page. You can ignore those, nothing happens in that direction. Of course, I'm assuming the table here is frictionless, so I'm going to get a net force like this. What's this net force equal to? Well, if I want to draw some angle, I might maybe call this angle, let's call it gamma. Why not? F net is going to be equal to 2, because they're two rubber bands, 2t, they're working in the same direction, 2t sine gamma. Now, one thing I could do right here is that essentially I make a small angle approximation in the same way we did for the pendulum. That'd be one way to tackle this. I say 2t times gamma in radians, and I track everything in terms of gamma. But I can also write the sine gamma as opposite over hypotenuse. So that's actually equal to 2t y over L. Right, because this length here is L. Yes, L tilde, but we said it's approximately equal to L, right? We justified it here. And so it's the opposite of this angle, that's the y position divided by L. It's my net force. Now, of course I've made a mistake here, because if y is positive, right, in the positive direction, which I called up positive, then the force is going to be down, whereas if y is negative and the object's down here, negative y position, when the force would be in the positive direction. We should have put a minus sign in front of this. Now you can almost see how this acts like a spring, right? It's essentially equal to minus constant times y, right? This constant is 2t over L. So this is my spring constant, right? F is minus kx, ky, who cares what you call your variables. The k in this case is 2t over L. So if I identified my k right here, this thing here, that is my effective spring constant k. Now, if you are more careful, right, you could write this would be y over L you replace by this expression here, and t you might modify a little bit too to accommodate for the fact that the string and the rubber band stretches. Then this would be a more complicated function, but then you could still essentially approximate its gradient close to a small y, and you'd get back to that result. In our case, we made this approximation, use this approximation that arises from the smallness of the oscillation, the smallness of the y value, directly up here already. I've got an effective spring constant, so now we are essentially done. So if I want to find the rate of oscillation, say the frequency, well, figure out what it is. Find the frequency. F I know is equal to 1 over 2 pi times k over m. Right, that's the spring result. But we've managed to rewrite the physics of this one in terms of the language of a spring, where we've identified a spring constant, the thing that multiplies the displacement to give me the force. Right? The steepness of the slope of the force versus position graph near small values of y, near y equals 0. We identified that, 2t over L. So just plug this in here. So in our case, I'm going to get 1 over 2 pi, and k is 2t over L, so 2t over Lm. So this is going to be the frequency of the oscillations as I'm pulling this up and down. Now I can change that. Now I can see I can change it, for example, by pulling the rubber bands tighter. It doesn't change the position of this. It's right in the middle. But it would, you can imagine if I pull those rubber bands tighter, maybe I move those blocks a bit further away, then it's going to oscillate faster, according to this equation. If I make the mass heavier, it's going to oscillate less, and so on. So this is an example of where we use the fact that the oscillations are small, that the y value is small, to make an approximation. In our case, we approximated that therefore the tension and the length L, right, that they are constant. And that led us to finding the effective spring constant. We wrote the net force as minus something, some constant, times the displacement. This is a spring, this is a linear restoring force. The effective spring constant K is 2t over L. So then all the math that we developed for the spring just carries through, and we get the frequency. Second example we could go through is the pendulum, but we already went through the simple pendulum, the string with a mass at the end. And that was really just an example of the small oscillations. And there we used the fact that the sine of an angle is approximately equal to the angle. That was the linear approximation. That was the part, that small angle approximation, that was the part where we approximated the actual shape of the force against the displacement graph by a straight line. Let's do a very similar example where we use that same approximation. Again, it's a pendulum. This time imagine a physical pendulum, like not this idealized ball at the end of a string. So this could be a rod, this could be some other kind of shape. I'm going to leave it general. It has some moment of inertia I, and by moment of inertia I mean, of course, around the pivot. Remember, a moment of inertia has to be defined around a particular point. Center of mass is right here. So this is where the weight acts. There's a mass m. The weight is equal to mg. Now, it doesn't take much analysis to figure out what the torque is in this case. The torque is going to be equal to m times g, the weight, times L, that little lowercase l is the distance between the center of mass and the pivot. So that'll depend on where do I put that pivot. Is it at the end? Is it somewhere closer here? It depends on the shape of that pendulum, right? Where is the center of mass? Is it bang in the middle? Is it further down? For example, if the bottom is heavier than the top. It depends. But the distance is lowercase l, and this is the torque, except I have to take into account directions. And now, if this here is some angle, let's call this angle theta, then hopefully you can see that the torque is going to be mgl sine theta. If you need to explain that, obviously the component of the weight that is responsible for torque is in the sort of tangential direction like this. I'm not going to draw it right now because it will just make the diagram too messy. This angle here is also theta. You can figure it out from there and confirm that this is indeed true. That's a torque. Let's call it what we usually call torque. Let's call it tau. Alright, so what's that equal to? Well, because it is the torque, it is going to be equal to alpha times the moment of inertia. So at this point, this is an equation that is not, that this torque here, right, this is not a linear equation. It has a sign of an angle. So we're going to do the small angle approximation. We're going to use that sine theta is approximately theta, the thing we've done before. This linearizes our, in this case, restoring torque. Linearizes the restoring torque. Now, if you're confused restoring force versus restoring torque, well, in this case, since I'm measuring the displacement of this pendulum by an angle, I'll have to talk about torque rather than force, but restoring torque is of course always towards the straight down equilibrium point. This is the point where I'm saying I've got a sine function. Oh no, that's complicated. Let me instead approximate it by a straight line. And it happens to be that the gradient of a sine function at 0 around theta equals 0, that is approximately equal to 1. So sine theta is approximately equal to theta. Let me just draw this again. I talked about it in the context of the pendulum. So here's my sine function, right? It goes like this and like this. But if you imagine I zoom in here, and I'm going to make this part bigger, right? It's this whole thing now. I make it bigger. Well, this section here is essentially a straight line. Of course, up here, what I should have included is the fact that that the torque really is in the opposite direction of the angle. If the angle is to the left, torque is to the right. If the angle is to the right, torque is to the left. I should have put a minus sign there. And if you then make this approximation, I'm going to get that minus mgl theta is equal to d2 theta dt squared. That's alpha. It's exactly analogous to when we talked about the pendulum times I. So again, I have a linear restoring torque in this case. I can just rearrange that. D2 theta dt squared is equal to minus mgl over I theta. And so I can identify my I can identify this part here as ultimately being equal to, we put it like this, this is essentially k over m, right? Because normally I have ma equals minus kx. Now if I imagine I take the m to the other side, then there's just one constant, which is this one here. And so this is my k over m. So that means I get that, for example, the angular frequency of the oscillation is equal to, that's the square root of k over m in quotation marks, which in our case is mgl over I. So again, we treat it a little bit different mathematically. We set up the equation of motion here, but again, by having this linear approximation of our function, that is gives me the force, or in this case the torque, I can identify an effective spring constant k. Okay, now let's look at the energy. side of this kind of approximation. To look at this kind of approximation from an energy perspective, I just want to focus on an example. I'm going to take a potential energy against position graph that has this kind of shape. Now, what does this represent? This is actually a very good model to model the potential energy involved in an ionic bond between two ions, right? You've got, say, sodium chloride, salt, right? It's a sodium and a chlorine atom, well, ion. They bond together, and in terms of the energy, this looks like this. So this, on the bottom here, you see the atomic separation. Now you can tell there's this point here. This is the lowest energy, which means if the two atoms, the system of two atoms is a fairly low energy, they have to be somewhere like this. So this would be the bond length. If you've done chemistry, it probably means a lot to you thinking about this kind of situation. Now clearly this graph as a whole, right, is not a quadratic. Remember, in the case of a spring, the potential energy is just a quadratic, effectively a parabola. But this point here is an equilibrium point. It has to be because it's the lowest energy. So this here is the equilibrium point. Because just to the left of it, meaning if the two ions are slightly closer than this particular distance, right, then they'll require more potential energy. If they want to be slightly further apart than that particular distance, they need to have more potential energy. So if you don't have enough energy, it means they're kind of trapped being down here. When you put a stable ionic bond, that's the situation. To break that bond, you need to give them a lot of energy. You shoot some photons, some light at them, give them energy that will raise the energy level up here, and they can leave. They can make it up this potential hill and never be seen again. Now, as I said, this valley here, this equilibrium point, it is not a quadratic. It's some other complicated function. Right, so this shape here it's not a quadratic. And the quadratic is what we want for potential energy of a spring, but it's not a quadratic. But you can probably guess what we're going to do. Let's just focus on small oscillations away from that point here, right? Around this point, the force that is associated with this potential energy here, whatever it is, we're not going to care like what exactly that interaction is. We just care about the shape of its graph. Around here, it is a minimum. It's flat, so there's an equilibrium point. I'm going to approximate this shape here as a quadratic. So I imagine I'm zooming in on this. So I'm zooming in. So here's my axis at the bottom. Right this way. And then I've got a graph that looks something like this. Now, as long as I zoom in enough, I will be able to approximate this shape in here as a quadratic. This is approximately a quadratic. Right. So all I have to do is have a look at the shape of this graph, and I have to ask, and there are mathematical methods of doing that, what quadratic best describes this, right? So I could write this as something times the displacement from this point squared, which I guess I should be writing r minus, so this is let's call this distance r0, right? The bond length here, r0. Remember, the position here labels the distance between the two ions, right? So this is kind of the equilibrium distance, r minus r0, so that is the distance if I'm over here the distance between here and here is the R value here, the separation, minus this. If I'm on the left, it would be a negative number. Right? If I choose in the big graph here, if I'm at this point here, then my distance from the bond length is the R value here minus that distance here, the bond length. So this thing here, I can figure this out from the actual shape of this, but that is going to be equal to 1/2 K. Because in a spring, the potential energy U is 1/2 kx squared, and my x, of course, is the distance from that minimum. So at this point, right, it fulfills the same requirement that we observed at the very beginning of this lecture. It's a minimum, so it goes up to the left, up to the right, it's flat. So what does it mean? It means that whatever the value is, the actual value of the energy doesn't matter. I've drawn it as 0, but that's irrelevant. What's important is that it's a minimum in the energy graph. So I can approximate this as a parabola. I can find the effective spring constant. Now I'm not going to actually work this example out in mathematical detail because it would get rather complicated. I have to figure out what function I can use for this, and which you can do, but I've done it before. It's a rather messy example. So I'm going to do a different example instead. An example that you may be somewhat familiar with. So here's the example I want to study. I imagine I have 3 charges, electric charges, and they're arranged that I've got 2 big ones. I imagine them to be equal just for simplicity. They're here and here, and they're fixed in place. They are not going to move. Then imagine I've got another charge right here of charge lowercase q. Doesn't strictly have to be doesn't strictly have to be smaller than either one of those, but it might as well be. And what's going to happen is this charge, right, is positive. The old positive, it's going to get repelled by this one. It's going to get repelled by this one. Now, so it wants to be right in the center where the force from both of them is equal. If it moves too far to the left, then the force from the one on the left will be stronger, so it'll get pushed back. If it moves too far to the right, the force from the right one will be stronger, so it gets pushed back. So this setup creates an electrostatic restoring force on this charge in the middle. Now we could analyze this in terms of forces. We're not going to. We're going to analyze this in terms of potential energy. So the only piece of information we need now is that the potential energy due to essentially 2 charges is the electric constant K times the first charge times the second charge divided by distance between them. Right? Maybe you remember that from a previous course. So that's what I've written down here. Now imagine this charge might be displaced a little bit to the right, or maybe a little bit to the left. I assume it's not going to go up and down. It'll be a different story. So I'm going to call the displacement of this charge from the center line, I'm going to call this x. Right? So if x is 1 millimeter, it's 1 millimeter to the right of the center line. That means the distance this charge has from this one here for an arbitrary x position is d plus x, whereas the distance this charge has from this one here is d minus x. Now x could of course be negative if the charge is to the left, right? But the total potential energy is going to be equal to the potential energy due to those two, their interaction, and the potential energy due to their interaction. Yes, strictly there's also the interaction between those two, but because those can't move, that's just going to be a fixed value. It's never going to change. It's never going to contribute anything to the dynamics of the system, because these are fixed in place by our assumption. So this is my energy. So let me plot this on a graph for you. So I went to the Desmos Calculator and I inserted the function that I just showed you on paper. Now I chose values, I had to choose some values, and I chose KQQ, so electric constant times little q times big Q to be equal to 5. It was arbitrary, I have to make some choice, only the shape is ultimately going to matter, right? So that if you compare this function to what you have on paper, that's 5. I decided the value of D, big D, the distance between the equilibrium point and each of the two big charges left and right, that's 10. Had to decide on something. Right? So I plotted those, and this is the function we get. Now strange things happen here, right? But that's because at 10, that value here, that's when I reach the other charge. So of course the potential energy there would go to infinity. Now I don't care about this because I'm constraining my motion to small oscillations. And around 0, around the equilibrium point, you can tell the potential energy looks like this. This is clearly not a quadratic, right? A quadratic doesn't have this sort of steep U shape, this sort of bucket shape, I guess, that we see here. Right. But down here is clearly an equilibrium point. It's a minimum. Here the gradient is flat. So I can approximate this as a quadratic. Now, I'm going to show you in the derivation in a second what exactly that quadratic what exact form the quadratic takes. Now I've already included it here, so I can show you all in one go. So it's going to turn out to be that there's a constant that's twice KQQ over D. So KQQ is 5, 10 is 10, 2 is going to follow from the derivation, you're going to see that. And then there's a quadratic term that turns out to be twice KQQ, K times little q times big Q, divided by the distance cubed times x squared, right? So I haven't shown this to you yet. You're going to see the derivation in a second. I've included it here so we can actually see how this approximates this function. So I'm going to just activate this. Now you can see the blue one here. The blue one is the quadratic, and that's the quadratic I am using to approximate this function here. The red one is the actual potential. The blue one is my approximation. Now, you can see that anywhere, say, between about -4 and 4, so about 40% of the way to the big charge is actually a really good approximation. Let me zoom in a bit. And now I'm zoomed in, and I mean, it's amazingly good, right? Here at now zoomed in to this degree, you can tell it's -4 here. So this is 40% of the way to the other charge. It's an extremely good approximation. If I assume my oscillations are restricted to about 10% of the distance between here and here, you can't see the other function at all. It's right there, right? But it's exactly the same. Like, you can't tell the difference. So this quadratic approximation, it turns out to be extremely good, and it's often the case, right? Only when I zoom out far enough, you can tell that those two are clearly not the same function. But it's this approximation that allows me to treat this system as a spring, provided that the oscillation remains sufficiently small that I can't tell the difference between the blue line, my imagined spring, and the red line, the actual potential energy function. Of course, this actual expression, haven't derived it yet, gonna do that right now. Alright, now I'm going to simplify this algebraically. This is going to be K, Q, Q, and I'm going to emphasize, right, K is the electric constant. It determines the strength of electrostatic forces. It is not the spring constant. Yes, same symbol, unfortunate. But we know what it means here, right? We've defined it as the electric constant in the context of this example. It's this 1 over d plus x plus 1 over d minus x. Okay, so I want to approximate this function. This is a function of x. You saw what it looked like. I want to approximate it as a quadratic in more generally a polynomial. Right, then I want to focus on the quadratic term. So let's do that. What I can do is the following. So here's, in a way, this is going to be part of your mathematical toolbox. I'm going to take out a factor of 1 over d. And I'm left down here with 1 plus x over d plus 1 or 1 minus x over d. Right, make sure you follow algebraically what I'm doing here. So this here is small, right? This part here is a lot smaller than 1. Because I'm assuming the displacement of this charge, left-right, is a lot smaller than that distance here. That is, in this case, what I mean by the oscillation being small. Of course, this is the same thing, so this is also a lot smaller than 1. So now I can use what's called the binomial expansion. And again, that's part of your toolbox as a physicist, or if you're in a related field of physical science. Use the binomial expansion. And the binomial expansion is in the back of your textbook in the appendix. You'll find it. I think it's page A2, or in appendix A2. And for this case, what we're going to do is we're going to approximate that 1 plus or minus, let me write it like this, 1 plus some small value epsilon. So I'm assuming epsilon is small compared to 1, because in our case epsilon is going to be x over d. That is approximately equal to 1 minus epsilon. And that in fact is already a good approximation. Again, check it. 1 over 1.1, is it 0.9? Close to it. 1 over 1 plus 0.001 is going to be very close to 1 minus 0.001. Try it. Turns out though we can be more accurate if I include the next term, plus epsilon squared. This is not the end, this is not exact. I would have to keep going and add more terms. But and if this is were a for this can also be approximated. Difference is that would look like this, and so on. Right, so I can approximate a function like that in terms of a polynomial that might never end, if I want to be exact. But it forms a good approximation, say even just to here, if I stop this here, provided epsilon is small, and that's my assumption. So let me plug that in. I do this, right? This is my epsilon here. I'm going to get that ux is equal to kqq over d times, I want to replace 1 over 1 plus x over d by using this here. So it's going to be 1 minus x over d plus x over d squared, and some more terms that are going to be smaller, right? Because this is already a lot smaller than this. Every time I multiply by x over d, it's going to get a lot smaller because x over d is much smaller than 1. Okay, make sure that makes sense to you, right? If x over d is 0.1, this is going to be 0.1, 0.01. The next term for a more accurate approximation would be 0.001. But maybe I don't care about being that exact. That's the first term, this one here. Now I want the second one. So I'm going to add to it 1. I'm going to use this expansion here. Epsilon is equal to x over d. 1 plus x over d plus x over d squared, and so on. Now we can maybe see why I decided to include the second term in my approximation, why I didn't just approximate it like this, because I can see that these ones are going to cancel out, ending up with k qq over d, 1 plus 1, that's 2, and these ones add, they have the same sign, plus 2 x over d squared. And technically there are more terms that are smaller that I am not including here. So now you can see how we ended up with the quadratic. Right? I made an approximation, and that's why I rearranged it in this way. It allowed me then to expand this, write this function that's complicated, write it as a polynomial, specifically as approximately as a quadratic. So this is what I've, what I guess you can see on the, if you compare the graphs. And so now I can read off what the constant is. So let me plot this by hand. Let me sketch it for you. So this function here, what does this look like? It has a constant, right? At x equals 0, it's not 0, it's somewhere like here, namely at 2k q over d. But then it is a quadratic, so it's going to look like this. So I can write this as 1/2 times spring constant. I can't write k because I've already used k to mean something else. Times x squared, right? That is the potential energy. Or in our case, that's equal to 4k q. Sorry, I'm doing 2. 2k q over d cubed times x squared. So I can read off that my spring constant, right, this 1/2 the spring constant is equal to this. So my spring constant is equal to 4k q over d cubed. So this is my, I say spring constant is the effective spring constant, right? It's not literally a spring. It's a charge stuck between two other charges, but it oscillates, provided the oscillations are small. So this approximation is good. It's fairly accurate enough. That implies that the effective spring constant is this. So what does this imply? This implies, for example, that the angular frequency with which it oscillates back and forth is equal to the spring constant over m. Right? So in our case it's 4k q over d cubed m, just by plugging in into the equation that I've derived for the angular for the angular frequency of a spring. Right, so again, the method was similar as it was for the forces. I take the actual function, which was this, and I approximate it by some technique or other as a quadratic. Now those techniques, binomial expansions and so on, those are things you learn about in your math courses. Most generally, the topic you want to be thinking about here is called Taylor expansions. All these expansions, the small angular approximations, binomial expansion, all these ways to approximate a function that's not a polynomial, not just a linear, quadratic, etc. Those are all approximated by what's called a Taylor expansion. And how to do this in general, well, I'm not going to present it here because that would take me probably several classes worth. But that's a very useful technique to actually study. Because then what we do is we approximate it and we just sort of match. We look at this and we're like, oh yes, this is a quadratic. The spring is a quadratic. I don't care about where the 0 point is. The 0 point being lifted up does nothing. It doesn't change anything. So I can just read off what the effective spring constant is. Like 1/2 spring constant is equal to, in our case, this. And so then all the things I know about springs applies as long as I replace the spring constant that I normally call K by whatever I've discovered here. And pretty much any time, right, you have an equilibrium point and a restoring force, you can approximate the force as a linear restoring force, or similarly approximate the potential energy as a quadratic. There are some mathematically odd examples you can come up with where that's not true, like a quartic without any cubed or square terms, but any physical example you'll be able to approximate in that way. And that is, to a great extent, why we are studying springs. We're studying springs not because we literally care about what a mass on a spring does. It's an interesting little bit, right? In real life, we don't have masses on springs, but we have little pieces of machinery that are oscillating. Right? Little things are displaced a little bit from the equilibrium position. A string that is taut, wobbling back and forth if someone plucks it. You take your finger and you sort of, I'm not sure what you call this, you hit a wine glass and it rings. Makes a noise. All these oscillations are approximated in this way, and that is why we're studying springs.